Good morning everyone. Today we are going to start electrochemistry. This chapter electrochemistry we can divide into three segments. The one is electrolytic cell, another is galvanic cell, and the third part is conductance in the solution. We can divide this chapter into three parts. The first part is electrolytic cell, which we will be covering in this session. Another part is galvanic cell, another part is galvanic cell. So these two are electrochemical cells, and the third part that we have to cover for the JEE syllabus is conductance. Is a conductance in the electrolytic solution. Conductance in the electrolytic solution. We are going to start from this session with electrolytic cell. So first of all, we should know what is electrolytic cell. Put the heading electrolytic cell. Put the heading in your notes electrolytic cell. What is electrolytic cell? First of all, few things should be taken into consideration. Electrolytic cell is a device which converts electrical energy into chemical energy. Electrolytic cell is a device which converts electrical energy into chemical energy. Point 1. Electrolytic cell is a device which converts electrical energy into chemical energy. Point 1. Second, what exactly is electrolytic cell? How it converts electrical energy into chemical energy? First of all, we should know that any non-spontaneous reaction cannot be carried out spontaneously. अपने आप नहीं हो सकती. एक non-spontaneous reaction एक ऐसी reaction जिसका given T and P पर delta G positive है, वो reaction कभी भी अपने आप नहीं हो सकती. It can't proceed by itself. Some external driving force can carry that process, and that external driving force is provided by this electrical energy. How it exactly works, we can understand by taking example of electrolysis of molten NaCl. So I am taking a simplest example of electrolytic cell, where in a beaker I have taken molten NaCl. It's a fused NaCl. It's a fused NaCl. Why fused NaCl is required? Because in solid NaCl we all know ionic compounds in the solid state are bad conductor of electricity. That's why molten NaCl is required, in which we can carry the electricity. Pass the electricity. Two electrodes are required. Two electrodes are required so that this electrolytic cell can interact with the external cell, with the galvanic cell. This can interact with the another galvanic cell. Next, so what exactly is electrolytic cell? What exactly is electrolytic cell? This is electrolytic cell. Electrolytic cell contains a beaker. In a beaker there is an electrolytic solution. In this case the electrolytic solution is fused NaCl, and we have put two electrodes. Electrodes may be of graphite, electrodes may be of platinum or any other metal. In this case we have taken a platinum electrodes. In this case we have taken the platinum electrodes. Now we are going to connect these electrodes with some external device. External device, say we are taking a galvanic cell. By this external device we are connecting this electrolytic cell. By this external device we are connecting this electrolytic cell. Now we should know that the electrolytic solution, electrode, the container, this whole device, this whole setup is called electrolytic cell. This whole setup is called electrolytic cell. This whole setup is called electrolytic cell, while this one is external device. This is not a part of electrolytic cell. This is not a part of electrolytic cell. Now what will happen within the solution? What will happen within the solution? We all know that this electrode which is connected with the positive terminal of the battery becomes positive and is called anode. And this electrode which is connected with the negative terminal becomes negative. This rod becomes negative and is called as cathode. Well, we know that the positive NS plus will move towards the cathode, while negative Cl minus will move towards the anode. If this current is passing on, if this is connected with the external device, otherwise no natural movement will take place. Then what will happen at the anode? What will happen at the cathode? At anode, Cl minus will migrate, and at anode the reaction taking place will be Cl minus forming half of Cl2 gas plus electron. What will happen at the cathode? These Na plus will go to the cathode. Well, no, we know that electrons are ejected. Electrons are ejected at anode. These electrons will be transferred to the cathode by this external device, through this external device, and these Na plus will accept the electrons at the cathode, and at cathode Na plus plus electron forms Na solid. What is the net reaction? What is the net reaction? Can we add these reactions? Why not? What is the net reaction? Net reaction, this electron and electron would be cancelled out, and the net reaction would be Na plus plus Cl minus forming Na solid plus half of Cl2 gas. This is the net reaction. We should know that this reaction which we are carrying out here, this is a non-spontaneous. Delta G for this reaction is positive. Delta G for this reaction is positive. This reaction can't be carried on its own. We need some external device, we need this external EMF source to carry on this reaction. So what is electrolytic cell? Electrolytic cell is a device which converts electrical energy of this cell, galvanic cell, into chemical energy of Na and Cl2. Or in other way, we can say that any non-spontaneous chemical reaction can be carried out with the help of electrical energy, and the device in which this is carried out is called electrolytic cell. So this is electrolytic cell. Now we need to understand the functioning of electrolytic cell, how it functions, what's happening at the micro level. So let's see. Electrons are ejected from anode and are moving towards the cathode by this external device. This is asked in JEE. Electron moves from anode to cathode in the external device, while within the solution, what's the flow? It's flowing from anode to cathode in external device. Internally, are they coming from cathode to anode? Then only circuit would be completed. It means that in order to complete the circuit, the flow should be something like that. Electrons released at anode travel to cathode by the external device, while within the solution the electrons do not travel, rather there is a movement of Na plus and Cl minus. So within the solution, not exactly electrons, but by some mechanism, charge is moving on. It means that charge is moving on within the solution, from negative charge is moving within the solution from cathode to anode. Then only the circuit can be completed. So it means that the electrolytic cell, in electrolytic cell, electron is moving from anode to cathode in the external device, while within the cell it's moving from cathode to anode by some internal mechanism. This was asked in JEE. Be careful, movement of electron. Next, there are few points we should remember about the electrolytic cell. This is a point is that net reaction is Na plus is, let's see the oxidation number of Na plus. Here it's plus 1, here it's 0. Cl minus, here is minus 1, here is 0. What does it suggest? It suggests that sodium is reduced while chloride is oxidized. So there is some electronic exchange. We can see here in the half reaction of anode, Cl minus is losing electron, Na plus is gaining electron. It means that somebody is losing electron and somebody is gaining electron. So why not they interact in the solution? Why they need to move towards this anode and cathode? Because this is a non-spontaneous process. They can't exchange this electron in this way. Rather, they have the affinity to go backward. The spontaneous process is backward. For forward delta G is positive. For backward delta G is negative. It means that sodium has a tendency to lose electron and go to plus 1. Chlorine has a tendency to accept electron and go to Cl minus. But we are driving it against their tendency. We are giving electron to Na plus. We are snatching electron from Cl minus, it can be carried only with the help of this external device. It means the process will be carried not in the solution but at the surface of electrode, at the interface of anode and the electrolytic solution. At the interface of cathode and the electrolytic solution, electronic exchange will take place. Electronic exchange is a surface phenomena. It is carried out only at the interface of electrode and electrolytic solution. It can't carry anywhere in the solution. That's why the surface of electrode, anode and cathode becomes very important, and surface treatment becomes quite crucial. Next point is that how to relate it quantitatively. How to relate it quantitatively. So very important concept required in the electrolytic cell is what? Number of moles of electron. We need to know few basic things. The first thing is that what charge on one electron is E. That is 1.6 into 10 to the power minus 19 coulomb. Charge on one electron. Point 1. Charge on one mole electron. Charge on one mole electron would become E into Na. This is the Avogadro's constant. And on solving, this comes out to be approximately equal to 96500 coulomb per mole in SI units, and this we call as 1 Faraday or 1F. This everybody should remember right now. That's the charge on one electron is E, we all know. Charge on one mole electron would be E into Na, where Na is Avogadro's number 6.022 into 10 to the power 23. Multiplying, we get it approximately 96500 coulomb per mole, and this is a constant. This constant is called as 1 Faraday. It can be referred as either charge on one mole electron or charge on one mole proton, because magnitude wise it would be same. Now we come to the calculation of number of moles of electron. How to calculate the number of moles of electron? Question arises, why we are interested in calculating number of moles of electron? Because we can easily relate number of moles of electron with the mass of chlorine. We can easily relate number of moles of electron with the mass of sodium. That's why it's very important to relate number of moles of electron with the mass. The first step is calculation of number of moles. It's quite simple, because we know that charge on one mole electron is 1 Faraday. If say we are passing any moles of electron, so how much charge we are passing? On one mole is 1 Faraday. On any moles it would be any Faraday. I am repeating once again, listen. I am saying that charge on one mole electron is 1 Faraday. Everybody is clear? Now charge on 1 mole is 1 Faraday, charge on 2 mole, 2 Faraday, 3 mole, 3 Faraday, n mole, n Faraday. So well, charge Q we know is what? Is current efficiency into I into T. And on the other hand, on 1 mole it's 1 Faraday, on any mole it's any Faraday. Hence number of moles of electron can be obtained as charge over Faraday constant, or current efficiency into IT over Faraday constant. So it's a very important formula, everybody should remember. That is, number of moles of electron is equal to Q by F, or current efficiency into I into T by F, where current efficiency should be taken in fraction. I is current in the ampere, T is time in the second, and F is a Faraday constant. Right side everything should be in SI units. This is current efficiency in fraction, not in percentage. If given in percentage, divided by 100 to get it into fraction. I is current in ampere, T is time in seconds, and F is Faraday constant, as we discussed here, is 96500 coulomb per mole. So say, if I have provided you I, T, F and current efficiency, you can easily calculate number of moles of electron, and now you can easily relate it that if 1 mole electron is coming out here, 1 mole sodium would be deposited. If 1 mole electron is ejected from anode, is releasing from anode, so correspondingly half mole chlorine gas should be evolved at the anode. Is it clear to everyone? Clear? Well, now we come to the next part. What we have discussed so far, we have discussed the introduction of electrolytic cell. We have gone through the case study where we were electrolyzing the molten NaCl solution. We have looked at the reaction taking place at anode, reaction taking place at the cathode, was a net cell reaction, and we also got some picture of quantitative estimation where we can obtain number of moles of electron and relate it with the mass of sodium and mass of chlorine or mass discharge at the respective electrode. Now we are taking another theory. We should know this is important theory, is called preferential discharge theory. Preferential discharge theory. Preferential discharge theory. What is this preferential discharge theory? Preferential discharge theory is quite a simple theory. It says that if there is one seat and there are two competitors, obviously the one having more potential, having a more tendency for that seat, is more deserving for that seat, will get that seat. That's simple. So if there are two candidates which are ready to release the electron, the one with the more tendency to release electron, the one having higher oxidation potential will be oxidized first, while the other have to wait for its turn. Similarly, if the electrons are coming out in the electrolytic solution through cathode, two candidates are there to accept that electron, then in that case the candidate having more tendency to accept that electron, or the candidate with the higher, or the species with the higher reduction potential, will get that electron. It's very simple. The species having higher oxidation potential will be oxidized first at anode, and the species having higher reduction potential will be reduced first at the cathode, and rest have to wait for their turn. So say, talking about anode. So number one for oxidation is what? Is lithium. Lithium has the highest tendency for the oxidation. Lithium to lithium plus electron. Lithium solid to lithium plus aqueous plus electron. No species can beat lithium in the entire periodic table when it comes to the oxidation. Lithium has the highest tendency for the oxidation. So it means that if lithium metal is present in the form of anode material, it will be oxidized first, while everything has to wait. So is the number one, is a numero uno when it comes to the oxidation potential. Anode oxidation potential, I am talking about oxidation potential, number one is lithium. Then followed by other active metals as block metals. Then some p block metal, we have aluminium solid to aluminium plus 3 plus electron. Then some d block metals, we have zinc solid to zinc plus 2 plus electron. We have iron solid to iron plus 2 plus 2 electron. We have nickel solid to nickel plus 2 plus electron. Some d block metals. The first is S block metals, then some d block metals. Right now we are talking about the oxidation potential. This is reduction. So it should be like that. Half of H2 giving H plus plus electron. E naught for this process we have taken as 0, and with respect to half H2 H plus plus electron E naught 0, we have taken all these entries. So all these have positive potential, means they have more tendency to release electron compared to H2 H plus. Followed by we have some inert metals, say copper to copper plus 2 electron. Is a Coinage metal, E naught value is on the negative side. Followed by we have iodide and giving I2 plus electron. Followed by silver, giving silver and plus electron. E naught value is very negative, is minus 0.8 volt. Followed by we have Cl minus giving half of Cl2 plus electron. We have in the between silver and chloride there is bromide also, but normally not asked, that's why I am not writing. And then it's water giving electron. This is important entry. Half of water gives 1/4 moles of O2 plus H plus electron, E naught value. If you look at the SRP table, this is on the upper side, but if you look at the preferential discharge theory, it's on the lower side, and this anomaly can be explained with the help of over voltage. This can be explained with the help of over voltage. Over voltage is not in JEE syllabus, that's why I'm not discussing it right now here. But everybody should remember that don't look at the SRP table. Water is below Cl minus. Water is not above Cl minus. Water is below Cl minus if you look at the preferential discharge theory. And very important, what lies below water? So say a species like sulfate or nitrate or other carbonate, phosphate, etc., which have negative charge. Despite having negative charge, they fall below water in the oxidation potential. That means they are not oxidized in aqueous solution. Water will be oxidized ahead of these species. That means these species will never be oxidized in the aqueous solution when water is present, because water is ahead of these entries. So I am once again repeating what is the preferential discharge theory. It says that species having higher oxidation potential is oxidized first, followed by the weaker one, followed by the lesser tendency, and this will happen in the sequence: first, second, third, fourth, fifth, sixth. So these are some entries which you should remember. H2 is a reference. Then the coordinate metals: copper, silver, gold is even below the Cl minus, and sulfate, nitrate, phosphate, you all should remember it is fall below water. That means water is oxidized ahead of these entries. They will never get a chance when water is present when it comes to releasing electron. So this was about the anode. Now let's talk about the cathode, reduction potential. What would be the sequence? Obviously sequence would be reverse. Now the lithium which was at the top of oxidation, lithium plus aqueous, would be at the bottom. Mind it, lithium solid was at the top of releasing electron, but when it comes to accepting electron, it's not lithium. The contestant is lithium plus aqueous, because it can accept the electron. Lithium will not accept electron. So lithium is nowhere in the race when it comes to accepting electron. It's the Li plus aqueous. Li plus aqueous can accept electron, no doubt, but what would be the E naught? This would be at the bottom of that reduction potential table. So well, let's talk about the cathode. Cathode, reduction potential trend. Obviously at the top of this list is fluorine. We have half of F2 gas plus electron giving F minus aqueous. This is at the top. Means that in most of the species in which we deal, F2 is at the top. Fluorine is most eligible for accepting electron. No other chemical species is close to fluorine. There are some xenon compounds which are ahead of fluorine, but they are not in our course, so I am not discussing them. The fluorine is at the top, followed by what? Obviously there are too many entries into it, but the number one is fluorine. Well, where is the chlorine? Obviously chlorine would be below it. Chlorine will be below it. There are other entries, but we are interested in important entries which we require. So reduction, F2 is at the top, followed by chlorine, followed by what? Followed by is a silver ion. Silver ion plus electron giving silver, followed by mercurous ion, Hg2 2 plus 2 electron giving Hg, followed by copper plus 2 electron giving copper. We have then H plus electron forming half of H2 gas. E naught is 0. Then we have nickel plus 2 electron. Nickel. We have iron plus 2 electron. Iron. We have zinc plus 2 electron. Zinc. Is the trend reverse what we have studied in the anode? Well, yes, it has certainly reversed. Cl2 plus electron, half of Cl2 plus electron, it's Cl minus aqueous. Ag plus aqueous plus electron, it's Ag solid, it's Hg solid, it's copper solid, H2 gas, nickel solid, iron solid, zinc solid. But here comes the important entry, that is water. Water plus electron, what we are getting? Half of H2 gas plus OH minus. This is important entry when solving numericals. For this one, E naught is close to minus 0.83 volt, minus 0.83. This is 0, this is minus 0.83, well below it. This was plus 2.87 volt, 2.87 volt at 25 degrees Celsius in water. Now falling 0, now further falling negative, minus 0.83. And what's important? What lies below water? What lies below water? So below water we have active metal ions, say magnesium ions, aluminum ions, we have sodium ions, lithium ions, and that's why when we have aluminum ion in the solution, when we have calcium ion in the solution, we have lithium ion in the solution, and there is water. Water will take all the electrons, they will never get the electron, they will be never reduced in presence of water, because their electron accepting tendency is below water. For water is minus 0.83, for lithium plus aqueous it's minus 3.05 volt. It's well below the water. It means that if we want to give them electron, we need to take the molten salt. In presence of water we can't give them electron, because water is more eligible for electron. Water will take away all the electrons. So this is the preferential discharge theory. Now we need to use this preferential discharge theory in the understanding the qualitative aspects of electrolysis in production of reactions taking place at anode and at the cathode. Which reaction will be taking place at anode? Which reaction will be taking place at cathode? We need to understand. How? Let's see. Well, we have gone through the electrolysis of molten NaCl using platinum electrodes, where at anode Cl minus was oxidized forming Cl2, and at cathode sodium plus was reduced forming metallic sodium. Now I am discussing case B. I have taken aqueous NaCl. This is not molten NaCl. This is aqueous NaCl. Now we are going to perform the electrolysis. What will happen right now? Tell me. What will happen right now? Tell me. Now there are two candidates for the oxidation, two main candidates for the oxidation. One of course is Cl minus, another is water. Well, I am not considering OH minus, because OH minus in a aqueous NaCl solution, pH 7 hydroxide and 10 to power minus 7 is good for nothing. Well, if you again look at the preferential discharge theory, who is more eligible for oxidation, whether it's Cl minus or water? Look in your class notes. Which is more eligible for oxidation? It's Cl minus. Cl minus is more eligible for oxidation compared to water when you look at the preferential discharge theory. Don't look at SRP table, mind it, this is the error. You will make error if you look at the SRP table. You need to look at the preferential discharge theory, which we have discussed just right now. Now the more eligible is Cl minus. So Cl minus would be oxidized at anode forming half of Cl2 plus electron. But what will be taking place at the cathode? At the cathode again there are two candidates. The one is water and second one is Na plus. For cathode, these are two candidates which can accept electron, because we know that from anode electrons are released, they are now coming into the solution by the cathode through external device. Now in the anode, there were anode section, the anode, there were these two serious contestants for the releasing electron. water was a failure, Cl minus will release the electron. Water is below Cl minus in oxidation in the preferential discharge table. Now here cathode, water is eligible for reduction ahead of Na plus. It means water will accept the electron, not the active metal. We know active metal, lithium, sodium, potassium, aluminium, magnesium, they are below water in the discharge table, in the cathodic reduction potential preferential discharge theory table. So water will accept the electron and will form half of H2 gas plus OH minus aqueous. Now here what is happening? Here chlorine gas is evolved. Here we are getting hydrogen gas, and in the solution what we are getting? In the solution, if you add this reaction, in the solution we are getting sodium hydroxide. In the solution are we getting sodium hydroxide? So this is one of the method of preparation of sodium hydroxide. If we electrolyze the electrolytic solution aqueous NaCl using inert platinum electrodes, at anode Cl minus is oxidized and at cathode H2 is formed, and the solution we are left with Na plus and OH minus. This is a method of preparation of sodium hydroxide. So this was one case. Now let's take another case. Say if this NaCl solution, say if this NaCl solution was not enough concentrated, say it was very diluted. Say I am talking about case C. This was significant concentrated NaCl, significant concentration NaCl. Now I am taking a dilute, very dilute NaCl solution. Very dilute NaCl solution electrolysis using platinum electrodes. Now what will happen? Now take it down. You need to take it down the reactions, because ultimate thing is the reaction. If you can write down the reactions of electrolysis, what's happening at anode, what's happening at cathode, you can solve any numerical. The core point is reactions of anode and cathode, and few important entries I will be writing, I will be discussing, so that you can handle the numericals as in JEE. So well, case A we have discussed electrolysis of molten NaCl. There was no competition at all. There was only one candidate Cl minus for oxidation. There was only one candidate Na plus for accepting electron. There was no competition at anode and cathode. But case 2 we have discussed electrolysis of aqueous NaCl. There was some little bit competition, because there was Cl minus and water for oxidation. Cl minus win the race. Cathode there was some competition between water and Na plus. Water win the race. Now case C. I have taken very dilute NaCl. If we are taking very dilute NaCl, then it means that Cl minus numbers will be negligible, and obviously the potential to release electron is a function of concentration also. If Cl minus concentration is decreased, then Cl minus will be no longer a threat to the water, and water will become a number one contestant for the anodic reaction. Hence, anode water would be oxidized. What would be the reaction? Half of water will form 1/4 mole of O2 plus H plus electron. This would be reaction at anode. Cl minus is now outnumbered by the water. Cl minus poses no threat to the water. Water wins the race. This is a reaction taking place at anode. At cathode, since NaCl is very dilute, Na plus number is very little, it is already tending to 0. So it's a water which will be accepting the electron. Water would be accepting the electron. तो अब बताइए क्या होगा? एनोड पर वाटर इलेक्ट्रॉन निकालेगा, कैथोड पर वाटर ही इलेक्ट्रॉन लेगा, तो नेट रिएक्शन क्या होगी? Add them up, add the net reaction. What will happen? Since they are in the same solution, H plus aqueous and OH minus aqueous, we can cancel out by this one water. We can cancel out the electron, we can cancel out the electron. So what is the net reaction? Half of water, what is the net reaction? Half of water is forming 1/4 O2 at anode, 1/4 O2 at anode, and the electron is traveling to cathode. What's happening out there? The water is accepting electron and forming H2 gas. So it's the electrolysis of water. So basically what's happening out here is the electrolysis of water. So is there any benefit of adding some NaCl? Well, surely, because we know that water is a bad conductor of electricity. We add some NaCl to it, we add some NaCl to it, certainly the conductance of the solution will increase. And if the conductance of solution will increase, we add some NaCl into it, conductance of the solution will increase. Then with the little work we can carry out this electrolysis. Now I am going to discuss a concept about the active electrodes. There are two types of electrodes, the inert electrodes and active electrodes. The two types of electrodes that are used in the electrolytic cell. So one is inert electrode, for example is a platinum, for example gold, or even graphite electrode in the most of the cases is inert electrode. Active electrodes, we have metal electrode, zinc electrode, copper electrode, we have silver electrode, we have calomel or mercury electrode, or we have standard hydrogen electrode. These are active electrodes. Hydrogen electrodes, these are active electrodes. Gas electrodes, active electrodes. Most of the electrodes are active electrodes. Inert are very few. So what is the meaning of inert electrodes and active electrodes? Those electrodes which do not interfere with the reactions of anode and cathode and let them take place as per the merit decided by the preferential discharge theory. Those electrodes are referred as inert electrodes. Inert electrodes, we should remember platinum, gold, graphite, etc. If not mentioned, we can assume electrode to be inert electrode. But there are few active electrodes. In fact, most of the electrodes are active electrodes. There metals, zinc, copper, silver, calomel, standard hydrogen electrode, these are active electrodes. What are active electrodes? Active electrodes are those electrodes which may directly or indirectly influence the reaction taking place in the electrolytic cell. Such electrodes are called active electrodes. Once again I am repeating, active electrodes are those electrodes which can influence the reaction taking place at anode and cathode. So such electrodes are called active electrodes. I am saying they may influence the reaction. It's not necessary they will influence, but they may influence the reaction taking place at anode or cathode at anywhere. So if active electrodes are there, we need to reconsider the preferential discharge theory. We need to again discuss the things. I am taking one case where I am going to electrolyze aqueous NaCl using active mercury cathode. This is a calomel cathode. Then what will happen? So far we have discussed three cases in electrolysis. Now we are going to discuss case 4, case D, that is electrolysis of aqueous NaCl using mercury cathode. Electrolysis of aqueous NaCl using mercury cathode. So see, well, now we are going to discuss electrolysis of aqueous NaCl using mercury cathode. Here is mercury cathode. Here is a mercury cathode. See what will happen. In the previous case, as you discussed, oxidation would be of chloride ion and water will be no threat. The oxidation will be of chloride. Cl2 will evolve at the anode. Anode पर Cl2 evolve होगी. What will be the reaction taking place at cathode? In the previous case where there was no mercury, reduction was taking place of water, not for Na+. But in this case, mercury is an active electrode. It has more affinity for sodium. Hence, what will happen? Mercury will give electron to Na+, it will be partial towards Na+, and it will not give electron to water. And what will be the reaction taking place at cathode? Cathode reaction will be Na plus electron in the presence of mercury would be getting NaHg amalgam. Reaction was asked in JEE in the passage. It's an important one. So anode Cl minus is oxidized, as we have discussed earlier. Half of Cl2 will be formed along with one electron, and at the cathode Na plus electron Hg forming NaHg amalgam. Is this trend can be explained by preferential discharge theory? No. So every student should remember this trend. Every student should remember this case. This is important. When mercury cathode, when active cathodes are involved, they may upset the trend. We are going to take some one or two more cases. So let me discuss those cases which are asked in JEE. The case E. Electrolysis of, now I am taking electrolysis of aqueous copper sulfate solution using copper electrodes. Electrolysis of aqueous copper sulfate solution using copper electrodes. Is the copper electrode active electrode? Yes. Copper electrode is the active electrode. Copper. This is anode, this is cathode. Going to electrolyze copper sulfate solution, aqueous CuSO4 solution. Well, now what will happen at the anode? Anode, there are for oxidation, there are now three candidates. Number 1, copper. Number 2, water. Number 3, sulfate. As we know, look at the preferential discharge theory. Water oxidizes ahead of sulfate. Sulfate out of the race. Now look at the preferential discharge theory. Copper and water both have negative potential, but copper has higher oxidation potential compared to water. So water loses here. Now copper to copper plus 2 electron. So at anode electron would be released and copper will be oxidized to copper plus 2. Now these electrons will travel to the cathode. What's going out at the cathode? Now cathode, for they are in the competition. We have copper plus 2, we have water. The two candidates are there for except the electron. So look at the preferential discharge theory in the cathodic section. For the reduction potential, it's the copper which oxidizes ahead of water. So copper plus 2 electron is the copper. So will the copper deposit? Yes, copper will deposit. So this is what's happening out there. Look again, copper is oxidized, copper is reduced. It means that copper comes from anode and ultimately passes on to the cathode. What about some impurities? You say if there was impurity of silver, so silver can't be oxidized ahead of copper. So silver in the metallic form will settle down here in the form of anodic mud, and this method is used in electrolytic refining of metal. If we need pure copper, so say from various metallurgical process, the copper we obtain may be of 98% purity. We can further electrolyze it, taking impure copper as anode, and the pure copper will be passed on to the cathode, and above 99% purity copper can be obtained at cathode. But say if in this case we were using platinum anode, then what? Say if this anode was not of copper, case F I am talking about. Say this electrode was of platinum. This electrode was of platinum. Then what? And of course the copper is out of the race. So oxidation, water or sulfate? Certainly water. Sulfate is out of the race. So oxidation will be of water. So reaction will be oxidation of water as we know. So water will be oxidized and O2 will be forming. O2 and H plus will be formed at anode. What about the cathode? Is the copper plus still in the solution? Yes. The copper plus will be reduced? Yes. But in this case, now the copper plus concentration will decrease with the progress of the time. The H plus in the solution will increase with the progress of the time. But in the previous case, there was no change in the copper plus concentration because copper plus एनोड से ऑक्सीडाइज हो रहा था, कैथोड पर डिपॉजिट हो जा रहा था, कॉपर प्लस के कॉन्सेंट्रेशन पे कोई चेंज नहीं आ रहा था। इस केस में कॉपर एनोड से सप्लाई नहीं हो रहा है बट कैथोड पर डिपॉजिट होता जा रहा है, तो सॉल्यूशन का कॉपर प्लस कम होता जा रहा है और सॉल्यूशन में क्या H प्लस फॉर्म होता जा रहा है, तो सॉल्यूशन में H प्लस बढ़ता जा रहा है, pH कम होता जा रहा है। लेकिन प्रीवियस केस में कॉपर ही ऑक्सीडाइज हो रहा था, कॉपर ही रिड्यूस हो रहा था, कॉपर के कंसंट्रेशन में कोई फर्क नहीं पड़ रहा था, H प्लस पर OH माइनस पर कोई फर्क नहीं पड़ रहा था, pH पर कोई फर्क नहीं पड़ रहा था इन द प्रीवियस केस। तो दिस इज अबाउट द वेरियस केसेस ऑफ इलेक्ट्रोलिसिस। नाउ वी कम टू द last part in this electrolysis is the Faraday's law, that is also in the JEE syllabus, so we need to discuss that Faraday's law. So put the heading Faraday's law. So Faraday's law are old experimental laws. So what Faraday said, Faraday's law, put the heading Faraday's first law. Faraday's first law of electrolysis. We are talking about Faraday's first law of electrolysis. It's quite a simple law. It says that W of material discharge, weight of material discharge is proportional to the charge passed through the solution. Weight of the material discharge is charge passed through the solution, and it's quite simple. Say if you are electrolyzing the molten NaCl, electron. Say that I am discussing case A where chlorine was evolved and sodium was deposited. Chlorine was evolved. So Faraday's law says that if more charge is passed, more chlorine weight will be released. If more charge is passed, more sodium weight will be discharged. This is quite a fundamental law. Now there comes the proportionality constant. Proportionality constant is what? Capital Z into Q. Capital Z is called electrochemical equivalence. This is called electrochemical equivalence. What is this electrochemical equivalence? It is simple. We can define it. Say if 1 coulomb charge is passed, the weight of material discharge is called electrochemical equivalence. How to define? Remember, it's quite simple. Say set Q equal to 1. Q equal to 1 means charge passed is 1 coulomb. It is a unit. 1 coulomb charge passed, then the weight of material discharge is called electrochemical equivalence. Electrochemical equivalence further can be given as E by F, where E stands for equivalent weight and F for Faraday constant, and equivalent weight can be written as molecular weight of material discharge over n factor of material discharge. Equivalent weight, we all know calculation, we already discussed that in the redox section. Equivalent weight is molecular weight over n factor. In the redox process, what is equivalent weight? Equivalent weight is molecular weight over n factor. Molecular weight of whom? Molecular weight of material discharge. In case molecular weight of chlorine, that's 71. In this case, molecular weight of sodium discharge. And n factor in the redox process is what? With a 1 mole material, how much electrons are involved? In this case, we can clearly see Cl minus giving half of Cl2 plus electron. So molecular weight of Cl2, it's 71. Molecular is n factor of Cl2. So n factor of Cl2, for half mole it's 1, for 1 mole it's 2. So number of electrons associated with 1 mole chlorine would be how much? 1 or 2? It's 2. So molecular weight in case of chlorine 71, n factor in case of chlorine not 1, it's 2, because we will be calculating it for 1 mole Cl2, not for half mole Cl2. But if you are talking about applying it on sodium, then it's quite simple, because Na plus electron is sodium. So we want molecular weight of material or atomic weight of material discharge is 23. N factor of sodium, for 1 mole sodium it's 1 electron, so there will be 1, not 2, is 1. So N factor at anode and cathode may differ, no issue with that, because you will be applying it at a time either on anode or on cathode. No issue with that. So we can summarize this as W is equal to molecular weight upon n factor over Faraday constant into Q. What about Q? Q we can say that current efficiency into I into T. So this is a Faraday's first law. Be careful about the units. Why? because molecular weight is generally in gram per mole, N factor dimensionless, current efficiency in fraction dimensionless, I in ampere, time in second, Faraday constant coulombs. If there is a mixing of CGS units and SI units, yes, this is in gram per mole. Normally we take it in gram per mole. So weight will be taking in the gram per mole. So weight will be in gram, will be obtaining. Molecular weight is gram per mole. Rest, this is a dimensionless, this is a dimensionless. Rest, all these are SI units. These are SI units. Current in ampere, time in second is 96500 coulomb, SI units. So there is a mixing, CGS, and this is in CGS. Rest are in SI units. They will be cancelled out. We will be getting molecular weight gram. So you will be getting this one in gram. Faraday's first law. This is used in electroplating. The numericals are asked in various competitive exams regarding electroplating. Electroplating, we know that cathode material is discharged. Say we have seen the previous case where copper was discharged at the cathode. Similarly, if in gold plating you want gold plated ring, we want silver plated ornaments, in that case we can connect that particular ornament that has to be electroplated with the silver or gold and make an electrolytic cell where the ornament should act as a cathode. Now on the cathode, the weight of material discharge can be obtained as volume of material coated into density of material coated. Volume in cc and density in gram per cc. Now volume, if the cathode is in the form of plate, so area of cross section in centimeter square into the thickness in centimeter of the material coated. So well, area of cathodic plate into thickness of material deposited, maybe gold or silver, whatsoever, is a volume of material coated into density of material coated into gram per cc. We will get the weight, and from this numericals are generally asked for regarding calculation of time or calculation of current strength I, something like that. But the basic formula is Faraday's first law, W is equal to Z into Q. Now we are moving towards the Faraday's second law of electrolysis. Faraday's second law of electrolysis is the extension of Faraday's first law. Faraday's second law of electrolysis is extension of Faraday's first law. So what is Faraday's second law of electrolysis? Faraday's second law of electrolysis says that when same current is passed through different electrolytic solution, same current is passed through different electrolytic solution. So in this case, there are two solutions connected in series, the two resistors connected in series. The same charge is passed through both the solution. Say this is silver nitrate solution where silver is deposited at the cathode. Say this is copper sulfate solution where copper is deposited at the cathode. Then what does this Faraday's law says? Faraday's law says that W is proportional to Q, or W is equal to E by F into Q. Well, Q is a constant, F is a constant. So we can say in this case W is proportional to E because Q is constant, same charge is passed through the solution. F is a Faraday's constant, is a universal constant. Well, in that case we can say that weight of silver over weight of copper is E Ag over E copper. So the statement for Faraday's second law will be weight of material discharged at respective electrode is in the ratio of their respective equivalent weights. Is it clear to you? Or in the other way we can shuffle it and we can say that WAg over EAg is equal to WCU over ECU. Now what it says? It says that weight over equivalent weight is what? Equivalence. Equivalence of silver discharge would be same as equivalence of copper discharge. Well, what a good equation we are getting. If we know how much equivalence of silver have deposited at this electrode, we can blindly say that same equivalence of copper would be discharged at this electrode, because equivalence of silver is equal to equivalence of copper. Weight over equivalent weight is equivalent. The equivalent of copper is same as equivalent of silver. So this is about the theoretical part of the electrolysis. So this section we have completed. Next section would be of galvanic cell.